Thank you. Thank you for everyone for coming. I'm a little intimidated. I'm not used to an audience of poets, and but I'm going to talk to you a little bit this evening about how language is organized in the brain. And in particular, I'm going to concentrate and try to give you the message that there is not just one language system in the brain. There are few interacting systems and networks, and differences in how individuals read poetry or maybe write poetry might have something to do with the balance between these different networks. So the language in the brain is in the left hemisphere. This is the left hemisphere. This is the right hemisphere. And these red areas that you see here are the areas of the brain that process language. So in most right-handed individuals, language is on the left. In left-handed individuals, 25% have language bilaterally and 5% have language on the right side. It's still an open question why language is organized in the left side of the brain. People think that maybe it has to do with the fact that it derived from manipulation with the right hand. So first came manipulating tools with the right hand, and the left hemisphere controls the right hand. There is a crossing of functions. And so the first thing that we had to do was name the tools that we were using. And so maybe language went along with the handedness. So we can think of language as one system that takes up most of the left hemisphere. But actually what I'm going to try to talk to you about is the fact that there are, and there's many more than three, but tonight we don't have time, so we'll go through three systems. So a system in the parietal and frontal lobes that you see here in red that is involved in phonology and speech and grammar. A system here that crosses hemispheres, really, that is for reading and writing. So it integrates between vision and sounds to make reading and writing possible. And then there is a system that has to do with semantics and vocabulary. So I'm going to take you through this, what I call the pathway to understanding. So basically it's how you find the name for an object or how you understand a word. So we can start with a stimulus that is auditory, like a word that you hear or a sound, or a word that you see, a written word, or a face, or a house, or a color, or something that you perceive with your vision. So the first thing that your brain has to do is to understand that this is a stimulus that is coming from the auditory system, and this is from vision. So there's areas in the brain. One is back here, it's called V1 for vision, and one is called A1, that is for auditory. And this is where the very basic information is first analyzed. So just to understand that a stimulus is visual or auditory. Then what we have to do is what I call here material-specific encoding. So we have to realize that this is a face and not a house, or this is a word that is written and is not a color, or that what we're hearing is a word and not a sound or not music. So a processing that is a little more than just understanding that is coming from the ear or the eye. And that is processed by areas that are around these very first stations. Then what we had to do is we need to integrate this information to know that what we're hearing and seeing maybe correspond to the same concept. And then, of course, if we're naming or repeating a word or reading a word, we have to produce it. So where are these things in the brain and how can we study them? In the last, I would say, 30 years, we had the possibility of using functional imaging. So you can imagine a person in a scanner doing a task, and you see areas of the brain lighting up. So these are the areas of the brain that light up when a person reads a word, and these are the areas of the brain that light up when a person repeats a word. And you can imagine that it's the same word that they're reading or repeating. So a lot of the neural systems involved will be the same. But the visual part or the auditory part should be different. So if you subtract one image from the other, you get this area for reading in the left ventral part of the brain that is being called the visual word form area. So this is the area that distinguishes one word from the other and is very important for reading, I would say fundamental for reading. If you instead compare repeating to reading, you get this area around the auditory cortex that is very important for distinguishing, let's say, a word that you hear from another one or a word from a simple sound. What about other visual stimuli? We're very interested in written words tonight. So this is the area that I showed you before, the visual word form area very important to recognize words. What about other visual stimuli like faces? And we've done many experiments to look at this. And the similar area on the right side of the brain, this is the left and this is the right, is involved instead in distinguishing one face from the other. And so what happens when we see patients that have trouble with these, have either degeneration or some kind of lesions of this area of the brain. And this is something that we do a lot at the Memory and Aging Center. We study patients that have had some type of brain damage, and we study their behavior. So if we think of a brain lesion, in this case, these are patients who've had a stroke in this area, and they have a lesion in this area that is involved in analyzing words that come through the auditory system. They're going to have trouble understanding words, and this is one of the oldest syndrome described in neurology is called Wernicke's aphasia. So patients have trouble understanding words and have trouble producing words, because if you think that you don't know really what the word is, you're not going to be able to select the right word when you speak. And so these patients speak a jargon. They put words together in kind of a salad, and they're very difficult to understand. What happens if there is a lesion, either a stroke or a trauma? In this case, they were tumors to these more ventral areas involved in recognizing words or faces. You have this syndrome called prosopagnosia that it can actually be also developmental. It can be also, there are children that are born with this trouble recognizing one face from the other. And I'm sure many of you have read the book from Oliver Sacks, The Man Who Mistook his husband for a hat, and this is exactly what he had. He had a prosopagnosia, trouble recognizing a face from another object. If the lesion is on the left side, then the dyslexia appears, so trouble recognizing written words. So if you think of our pathway to understanding, we have these early areas that analyze auditory stimuli or visual stimuli, and then we have these other areas close to it that are important to recognize spoken words or written words or faces. But then at the end, we need to integrate this information, because the semantic information, the knowledge that we have about, let's say, Bill Clinton, is independent from the fact that I'm hearing his name or I'm seeing his picture. And so there is another system that I think Bruce will talk more about it in the anterior temporal parietal lobe, that is really more involved in knowing what the words mean and in our vocabulary, or in knowing from a picture or from a spoken word what that concept is, what is the meaning of that word. So this is this system that is involved in vocabulary and semantics. And this is the temporal lobes and this is the parietal lobes on the left hemisphere. So what happens when this system is lesioned? So I'm just going to show you what happens to the reading system, and I'm going to give you an example. I think Bruce is going to talk more about the general semantic problem. Let's see if I can get it. So you'll see this lady that we've seen at the Memory and Aging Center reading words that are spelled irregularly, exception words, or words that don't exist but that can be read using the phonic rules of English. Let's see if I can get it started.
Bury, yacht, flannel, tail, wolf, Iceland, wedding, chicken, colonel. What is colonel?
So she's also telling you what is colonel. She doesn't really know what that word means. So,
some people may not have heard that.
how did she describe the word?
Yeah.
Yeah, she didn't know what, she said colonel, and then she said, what does that mean? So part of this system of knowledge is knowing how irregular words are spelled. She reads like an Italian, like I read when I was learning English. She just applies the rules of phonics, but she's lost the knowledge that this word is actually read like, has to be read like yacht. If you read it using the phonics rules, then you read it as yacht, like she does. But using those rules of phonics, you can actually read words that don't exist, just normally as we would read them.
Snipe, Hans, Poach, Smode.
And so this takes us to an important model of reading, and there's a lot of big words here that you don't need to worry about, but just think about the fact that there's two ways of reading. There is one way in which we read words that we already know that are spelled irregularly, and we just read them automatically, and we have to know them, and we have to know the concept attached to them. So our patients who read yacht as yacht actually lose the knowledge. I've lost the knowledge of what that word means. Or we can use the rules of phonics and just read applying the rules that we've learned as children. And actually, that type of reading is often impaired in developmental dyslexia. So children with developmental dyslexia have trouble reading using the phonics rules. So they might be able to memorize the words that are spelled irregularly, but they have trouble using the rules of phonology. So the second route in which we're using the rules of phonology, the sounds, is actually the blue route that I was showing you at the beginning. So this route is really important to take us from vision, from seeing a word, to pronouncing its sounds. So I've called it the reading and writing network, and it helps us read without, even without the meaning, just applying the rules, the sound rules. And children use this route when they learn to read, when they sound out. And then they become more proficient, and automatically this network is used less, and it becomes more of an automatic process. So now we recognize our words, either from vision or from auditory stimuli. We know what they mean, and now we need to pronounce them. So the last system is a system that translates the sounds into articulation. And actually, speech is the most difficult and precise act of motor control that we do. And I'm going to show you an example. This is kind of an MRI cartoon of someone speaking. I think you'll recognize what happens.
She had your dark suit in greasy wash water all year.
So I'll show it again. You can see the tongue moving.
She had your dark suit in greasy wash water all year.
So you can see what a tightly controlled system is. I mean, if we think that moving our finger like this is a difficult motor task, you can understand that this is much more complicated than that. And so often trouble with speech are the first symptoms of diseases that involve then later the motor system. So this system involved in translating the sounds, segmenting the sounds of words, and really taking each sound and make it into a movement is this system up here in the parietal and frontal lobes. And we have patients who have difficulties in this semantic vocabulary system that are super fluent. They speak super fluently and fast. They can really, these two things can really dissociate. And on the other hand, we have patients that have trouble with speaking whose vocabulary is really spared. Saying that it's a highly interactive system, I wanted to show you one of our newest pictures. I couldn't resist showing it to you, of all the connections between the areas to give you an understanding that these are not isolated systems. They're interacting with each other all the time. So in summary, what I wanted to talk to you about and show you is that we have a highly specialized, basically half of our brain, almost half of our brain is devoted to language. That there is not one language system, but there are many. And that individual differences in these networks, there are individual differences that we see with MRI. Some people might have increased connectivity or increased volumes in one of these systems compared to the other. And I think that maybe you poetry experts could even think about some of the poets or some of the writing of people that concentrate more on the sound of words or concentrate more on using words with particular meaning together, or how, and so maybe some style of how poems are even written or at least read can depend on how these networks are organized in the brain. And then lastly, these systems are necessary, are the machinery for language, but definitely not sufficient. And I wanted to thank everyone who's participated in this work.